So in this class, we'll try to see what are switching frequency components in a power electronic circuit. So let's start with a very simple circuit in which there is no energy storage element at all. I have a battery source and a simple switch is connected to a resistor. So let's measure the voltage across this resistor when this switch is being turned on and turned off with some duty ratio. So duty ratio is defined as the turn on time divided by the switching time interval. Basically, we assume this switching time interval Ts to be constant. So that gives us what? The switching frequency. So we define switching frequency as 1 by Ts. Now when I switch this circuit, what would I expect across VR? So my VR is basically a pulsed voltage, right? So this time period is what I'm calling as Ts, and this is T on. The peak value is Vg. So we can compute the Fourier analysis, Fourier series for this VR. So that VR, voltage across the resistance, is equal to A naught plus n is equal to 1 to infinity. Let us assume it's even symmetric. Okay, so basically then this should be Ts. Okay, just a small modification in order to make things simpler. I just want to express the Fourier series only in terms of cosine terms. So I am introducing even symmetry into the signal. So n into omega s into t, isn't it? Now so A naught, we can easily find out that it is just 1 by Ts integral minus t by 2 to t by 2 Vr into dt. That would simply result us in 1 by Ts into Vg into T on, which is nothing but d into Vg. Now okay, just a second. Yeah, so now we can similarly compute an is equal to, since it is an even signal, I'm just writing out the definitions of the Fourier coefficients here. But the point I want to make here is the following. So basically I will get this down to be, you can check these things, 2 Vg by Ts into sine of omega s n t divided by n omega. It's just the integration of cosine, and I'm applying my intervals where it is non-zero, where the signal is non-zero. Okay, so finally I can express this as a Fourier series, that is equal to dvg plus sigma n is equal to 1 to infinity 2 vg by n pi into sine n pi d into cos n omega st. What is n omega? What is omega s here? Omega s is nothing but 2 pi fs or 2 pi by ts. So this is what our an is, and this is what our a naught. So if we draw the spectrum of this particular expression, I mean if you draw the Fourier coefficients and their magnitudes on the frequency axis, so what you can observe is we surely have a component of d into vg, and similarly the other components are at omega s and n omega s. So let us say this is our omega s, and based on the Fourier coefficient we can see that the magnitude is a decreasing function of n. So we have several other components at omega s, 2 omega s, 3 omega s, and so on. So the only desirable property or the only desirable quantity that we are interested in is this. Why? Because we are trying to control the output voltage using the parameter D. So here usually what our objective will be is we have some supply Vg and we want some other voltage Vo which can be controlled based on the application. So this is my switching network here. So how can I filter out these components? So when I say filter out, I should be designing a filter in order to provide a very high impedance to these particular frequencies. So what I would expect is a filter whose gain crossover frequency